In this video, we are going to study the rate of growth, and that means is how much the time requirement or the memory requirement of our algorithms grow with the size of the input data. So we just saw in this exercise that if we count every single time unit in this algorithm, we will get this function, and this function depends on the size of the input data. Following this rule is 21n, n is the size of the array, plus 22. The problem is, and you might wonder, this is too tedious, it's error prone. What if I missed one memory access? What if I missed one numerical operation? I'm going to get a quite different function, and I really wouldn't like to work like that. There's no other way. Besides, the RAM model is already very rough. We have made such big simplifications on the real computer that being so meticulous in counting the time units, maybe it's not worth. So if you are wondering this, you are right. And let me show you another reason why we don't need to be so meticulous in counting the time units. Imagine that we have two algorithms. One takes this amount of time, and the other one takes exactly the double amount of time. They are both linear, they both grow linear. In this graph, I have a logarithmic scale here and here, so you can see big and small numbers in this space. And here I have the numbers. So n goes 10, 100, 1000 in powers of 10, and you can see what the values of these two functions are. So if this was a representation of the execution time, you will say, well, for sure I would choose this algorithm because it takes half of the time than this. Now, both grow linearly, which means that if n is the size of the array, gets 10 times larger, then you will get an execution time that is 10 times longer. And that's okay. So far we can see that the constants are important, but let me show you what happens if, I'm getting ahead too soon. So if every time unit is 1 microsecond, these algorithms will take this time. So you can see one is the double of the other, but they are still in the same order of magnitude. So one is 35 minutes and then is 70. But what happens if we have a second algorithm that takes quadratic time to be executed? So the time does not grow linearly like this, it grows quadratically with the input size. So if we draw these lines, you can see that an algorithm that takes a quadratic time the time of that algorithm grows much, much faster than the linear ones. And if we translate these numbers into time, if every time unit is equivalent to 1 microsecond, look at the difference. We have 35 minutes for 10 million, for an array with 10 million elements, 35 minutes, 70 minutes here. But with the quadratic equation, you have 300 years. Gosh, that's a lot of time. We don't want to, and we can't wait 300 years for something, for an algorithm to finish. So the difference between linear growth and quadratic growth is so big that it seems that taking care of these constants and these details is not worth. So let's see what happens if we just drop the constants. So here I have just n and n to the square. This is the time, it's not the time units anymore. That will be an estimation of how much the time will grow. So here we are in the order of magnitude of 7, but here we are in the order of magnitude of 14. If that doesn't tell you anything, let's look at the execution times. You will see here that this will take 17 minutes, but this will take 30 years. So even when we drop the constants, And in doing so, we are losing precision for sure. But remember that our model is already rough. Even when we are losing precision, the difference remains very big. So in terms of comparing algorithms, maybe it's worth just dropping the constants because they are not adding much more information to our problem. So when comparing algorithms, constants can be dropped. But remember, we can drop the constants because we are comparing algorithms. We are not calculating precise execution time. If our problem would be to calculating precise execution times, then we should go for another quite different approach, okay? So, okay, we can drop the constants. That's good. What about lower order terms? Let's say that we have one function for the time that is n to the square, and we have another algorithm whose function for the time is n to the square plus n, and this is a lower order term. If we calculate this for these different values of n, you will see there's no difference at all. This value is so small compared to this that we really don't need to worry about this. So in summary, we are focusing on comparing algorithms, not on calculating precise execution times. And also we are comparing algorithms for big values of n, because when the values of the input size is small, really any algorithm is going to be okay. So if you have just an array of 10, if you see here n squared and n, they don't really make any difference. But when we really have problems is when we have big data. And in that case, we want a really fast algorithm. So if we are focusing on comparing algorithms for big values of n, then we can drop the constants and we can drop the lower order terms because we are focusing on the rate of growth. And to finish, let me show you typical rates of growth. So the black one is log n, the red one is n, and the green is n log n. These three are really good. If you have an algorithm that has these rates of growth, you are having a really good algorithm. These other three are examples of not really good rates of growth. They really grow so quickly that quickly you will have problems. This is n to the square, this is n to the 3, and this is exponential growth. So we can't even draw the third point because it's already so outside of our graph. So this is for now. The takeaway message here is when you analyze algorithms, do not care about constants, do not care about lower order terms, because when we are comparing algorithms, what we are really caring about is the rate of growth. Bye for now.